do here next up is to help others who, without that, I'm going to talk as briefly as possible, and I hope that we can save some time for a roundtable discussion.
Had their encore cut so that they could come on. And we're doing a Beatles song. About a year ago, there was a debate in this room between Pete Worden, anti-SSD, and somebody else. And Pete Worden cleaned the clock, based on work done by Federer, a paper done by Federer about 8 or 10 years ago, that said that SSD is multiple orders of magnitude away from feasibility, economic feasibility, and therefore deserves no R&D money. And what I've done, spent nights and weekends, this is important, this is nights and weekends work, this is not my day job. I think I found a way to break that. And here's the Beatles song. This first thing here, on the left there is a vehicle that is climbing a tether. You can't really see the tether, and it is climbing it with power from an IR laser beam. Okay? That's one of the two technologies I'm going to talk about to reduce the price by a large amount. The second bit is the Icaros satellite. It's launched by Japan. It's on its way to Venus. And if you look very carefully, you can see some yellow stuff here. Those are thin film solar cells. The total thickness of the cell plus the backing is 32.5 microns. It weighs practically nothing, and it produces at 4% efficiency about 500 watts power. So the total mass per kilowatt I've calculated to be approximately 800 grams per kilowatt of power produced on orbit. And by combining these technologies, I think that you can build a system that delivers about 5 watts, given a single launch, 5 megawatts, given a single launch, that will cost you a few X, 3 or 4 or something, the cost of doing a similar size of nuclear power per watt, with a bit of R&D. And there are niche markets where you might actually conceivably make a profit or come close to it. Okay, so the big problem in my mind is the same problem that John showed. The Powersat designs, particularly looking at the older ones, are just too big. And the reason they're too big is that if you send your power to Earth in the microwave from GL, you end up with enormous antennas. For these parameters, you end up with, say, a kilometer-sized antenna in orbit and a 10-kilometer receiver on the ground. If you have a kilometer-sized antenna in orbit, it makes no sense to have a small satellite. You need a great big satellite. That's a big problem. You end up with these enormous systems, so that even if you could do collector mass at 5 kilograms per kilowatt, which is a target that Federer said was really, really hard to get to or impossible, because ISS is, I think, 60 or 70 kilograms per kilowatt. I might be wrong on that. You end up with these enormous masses. You have hundreds of launches, and it's never going to work. Okay? So the first step is we need to get rid of that enormous antenna. This tells you how to do that. And I believe if I pick the right stuff how to make this slide, came to the same conclusion. If you send your power in the microwave, oh, by the way, this is wavelength, logarithmic, and this is atmospheric absorption. That's great. You have a nice big fat window and you can send lots of power through. However, your wavelength is on the order of centimeters. Now I want you to notice that right here there's a window right around 1 micron. It's not as deep, but it's pretty deep. And here's why that's important. Many of you will know this, but a few of you probably don't, so I'll go over it. This is the same basic idea, only the opposite. This is transmission, so you can see a little more detail in the 1 to 2 micron range. There's a couple of places that narrow beams can get through the atmosphere. Not going to get through rain, not going to get through dust, but there's a lot of deserts that have a lot of need for power. LA, for instance. And here's the thing, is that if you take the product of the diameters of the antenna, the minimum size that you can get in your basic physics is linearly dependent on wavelength. So if you go from 12 centimeters to 1 micron, you get a reduction in size of a factor of 120,000. That's a lot. In fact, it is the size goes down so much that you can, in principle, make something with a 5-meter beam on orbit, 32 meters on the ground. That's too dense. You get too much power. So if you want to get 5 meters to the grid, you make reasonable assumptions, and you send power down at 10x sunlight, you end up with a receiver about the size of a football field. And something reasonable on orbit. Okay. The reason that this we know this can be done in short distance with small amounts of power because NASA had a power beam competition. A couple of groups were in it. A lot of people successfully did this. laser motive 1. Here's some of the parameters. The important thing is they got 500 watts delivered over a kilometer of actual power in an operational setting, and they had about 10% overall efficiency. Now, if you talk to the folks who did this, they will tell you that if you can take stuff more or less off the shelf today and get maybe 25%, and it is completely plausible that with some decent R&D, and I verified this with some other stuff that we in the paper, you might be able to get up to 40%. That compares to 63% that was for the reference design, but I'll willingly pay that 20-25% for efficiency if I get 120,000 factor reduction in size. Oh, here's the setup, by the way. It's a helicopter holding a tether, and the thing climbs it with the microwave, infrared beam. The other piece, okay, now we've got a satellite that's reasonably sized, hopefully, with some R&D. Now we need to get the mass of the collecting area that's collecting the solar power down as much as possible. And I believe this is about as low as you're ever going to get. This is a heliogyro. It has no structure. The total structure of the system are 4 cables, here, 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 and this holds its shape by rotation. This is used as a solar sail, so it's reflected. What we want to do is take these guys here, these are, as I said before, these are thin film solar cells, and cover the entire surface. This gives you an idea of the size. And in doing this with little calculations, these solar cells are using maybe 4% efficient. It's running out about 45 grams per meter squared. It's only 32.5 microns thick. The power production, the rest of the sail is only 7.5 microns thick. That means you're getting about 800 grams per kilowatt. That's low. That's a sixth of what Federer thought couldn't be done. If you simply took exactly the same die, which cost only $16 million to build the first time, and only weighs 300 kilograms, so you can launch on a very reasonable vehicle, you get almost 10 kilowatts. But these yellow things out here are not power production. They're actually used to demonstrate some control systems that should work. The spin rate is quite reasonable, and the bottom line is this has some implications for this just goes to the calculations of how I got the amount that I did. Since we want to have some questions, we will go on. The implications are, just some very simple calculations, which I hope I haven't screwed up, but a bunch of people have looked at this and nobody's found anything wrong yet, is if you take one Falcon 9 launch, and I chose Falcon 9 because you get the price and the mass on the way. They claim it will give about 5 tons to GTL, and I'm going to assume you can fly the rest with what you've got, for $56 million. If you can do 5 megawatts to the grid, which I'll show why I think that's the case in a moment, that's $11 a watt to install power. But nuclear power, right now today, plants that are selling, if you include the lifetime cost, run you, depending on what you count and how much you like nuclear power, anywhere from $14 to $20 a watt installed. So it's in the ballpark, but that only buys you a launch. However, a few years ago, before SpaceX was able to actually talk to people who could get things done, they claimed that if I would buy 100 launches from them, I asked about 1,000 launches, but they mentioned 100, they would reduce the then price of the Falcon 9 by a factor of 3.6. So if you wanted to launch a lot of these, and SpaceX would still give you the same deal, which is plausible, not necessarily the case, then you would have that 3.6x to spend on the satellite, and you'd still end up with the same price installed per watt. Now, if you assume 100 grams per meter squared of the system, the total system, which is 45 grams for the collector and about 2.5 tons for everything else, which may not be enough, but at least it's plausible. It's not like we've got 100 kilograms left to do the laser and everything else. You end up with a system about 200 meters on the side, and if you assume 8% efficiency, that's sunlight on the ground, that's 20% conversion in space, which is consistent with the best in the lab, thin films that are around today, and 40% to get to the ground, which we went over before, you end up with about 5 megawatts to the grid. Now, if you sell that to bases in the middle of Afghanistan, where they really don't want to truck in fuel because the Taliban blow them up and kill people, and not to mention have a variety of problems, there's good reason to believe they'll pay at least $1 kilowatt hour. That was published by a study of a lot of others. Reason to believe it might actually be quite a bit more. That will give you enough to pay for your launch in about a year, if you can pull all this off. It's optimistic, but it's not, out of. So, hopefully we won't be in Afghanistan by the time this thing flies. That would be nice, wouldn't it? The highest priced power I can find is 29 cents a kilowatt hour in 2008 for industrial power in Italy. And that would be $13.5 million a year. It was a big deal for water, but it's not really out of the ballpark. Here's what you don't need. This is, I think, really important. You don't need a new launch vehicle. It would be really nice, but you don't need it. You don't need teleoperated robotic assembly. You don't need huge chunks of land. Football final size things will do. And you don't need to go to the international community and get radio frequency assignment, which could be a real problem. Here's some suggestions for IR power research. In the interest of time, I will say the one thing that SSI can probably afford and would really make sense to do is to fund system-level designs, and perhaps John is actually working this, I suspect he is, of how to do the IR power meeting, because that's really the key to getting the size down. I also think you really need to start looking at environment and safety, because if you understand the environment and safety issues up front, you can engineer around them. If you have to put it in later, it's going to cost you a fortune. And you don't have to put it in anyways. In terms of collector research, the first thing is, what would it really cost to turn the Icaros into a demonstrator? Okay, around roughly 10 kilowatt demonstrator. If you want to deploy a 200 meter sail, the deployment is strictly on solar sails, and the techniques used for a 14 meter sail may not work. We'll take a look at that. And I've done a little investigation in in-orbit maintenance. When you have a super light system like this, the photons actually blow it around. At 100 grams per meter, STK, in a year, all the forces null out. You get 0 for the first year. But you do get fluctuations during the year. At 100 grams per meter squared, STK simulations can say, oh, it's not too bad. You get back to right about where you were when you started, so you won't be too much station keeping fuel. You move around, but you need something to aim the beam anyways. However, if you get lower, around 20, you're blown away. The inclination goes to 10 or 15 degrees after a year, and the whole system goes unstable. The conclusion, everybody knows what the conclusion is, and I will skip that in the interest of time. Thank you very much.